Chapter 19 has three major components to it. It has a section on strategically making carbon-carbon bonds. It has a section on redox reactions, including a bunch of review reactions and a few new ones, and a section on protecting groups using the types of reactions we've already seen. Now, when we go to make carbon-carbon bonds, and this is a review, we have to have a nucleophile that's based on carbon and an electrophile based on carbon. If it's an electrophile based on carbon, it has to have a delta positive. So, for example, a carbonyl carbon is a delta positive, and nucleophiles will want to approach it. The beta position of an alpha-beta unsaturated carbonyl is delta positive along with the carbonyl, and some nucleophiles prefer to add 1,2, some add 1,4, as we saw in Chapter 17. The carbon attached to a leaving group, something that can leave as a weak base, it has a delta positive on it. Normally we think of those as the halogens, bromine, chlorine, iodine, tosylate, mesylate, and triflate, sulfonate leaving groups. And finally, alcohols have been one of the ones we've seen as leaving groups, but the OH itself usually doesn't want to leave without the help of something else, such as a strong mineral acid, H+ from H2SO4, or a specialized reagent that helps the OH leave as a neutral species. On the other hand, our nucleophiles must have a minus or a delta minus. Most recently, we've seen enolate ions that have a minus at the alpha position. Very early on, we saw terminal alkynes that can lose a hydrogen and become a negatively charged nucleophile. Cyanide ions are a nucleophile on carbon. And our organometallic reagents, alkylithiums, alkymagnesiums, and dialkyl-copper lithiums, all act as if we have a carbon minus at this position. The biggest difference between these is the alkylithiums and alkymagnesiums tend to add directly to carbonyls, and dialkyl-copper lithiums are less reactive, adding primarily to beta positions. Alkylithiums and alkymagnesium bromides don't work well in an SN2 reaction with alkyl halides, but it turns out that our new friend dialkyl-copper lithium does react with alkyl halides via SN2 reactions. In this chapter, we get introduced to a term to explain a concept we've used before, Umspannung. It's just a German word to describe that you can change delta minus or minus versus delta plus or plus by doing some simple chemistry. So, for example, normally carbonyls are delta plus, but the alpha position when treated with a base becomes negative. That's an Umspannung. You've changed the nucleophilic electrophilic character. The most common example is starting with an alkyl halide and making an organometallic reagent, because that's how these organometallic reagents are made. So, for example, if you treat an alkyl halide with magnesium, you're going to make the corresponding Grignard reagent. If you treat an alkyl halide with lithium, you're going to make an organolithium reagent. And as you learn in lab, this really means adding the metal directly to your alkyl halide and stirring it around and maybe providing a little heat to get the reaction started. Finally, if you want to create one of these dialkyl-copper lithium reagents, you actually do it in two steps. First, you make two equivalents of the alkyl lithium reagent, which you then treat with copper iodide to make one equivalent of the dialkyl copper lithium plus one equivalent of the lithium iodide salt. So the idea of Umspannung is that we change the delta positive on the alkyl group into the equivalent of a nucleophile, a negative. So we change its reactivity. Now, part of the chapter is about strategically making carbon-carbon bonds and dissecting products of carbon-carbon bond formation. Our warm-up exercise on Monday the 26th will address this, as did the bonus question from the last exam. There's also an old video I have about pulling apart aldol products that begins to address it. But in general, when you see a product of a carbon-carbon bond formation, there's going to be some lingering functional group right near where that carbon-carbon bond was made. Another major topic of Chapter 19 is oxidation and reduction, and we've already seen some of this in prior chapters. For example, we've seen things that have carbon with 3 bonds to oxygen be reduced to carbons with less than 3 bonds to oxygen. For example, we use the reagent lithium aluminum hydride to take something of a carboxylic acid level and reduce it through an aldehyde all the way down to an alcohol. We can also take an aldehyde, react it with lithium aluminum hydride or sodium borohydride, and get to the alcohol. Those are all called net reductions and often symbolized by a hydrogen bracket. This could include a whole number of reagents, most of which have a lot of hydrogen in them, often with metals. Likewise, we saw in a previous chapter that ketones can be reduced to give secondary alcohols. Notice that the carboxylic acids form aldehydes or primary alcohols. If you start off with something with 2 bonds to carbon and 2 bonds to oxygen and you reduce it, you can go down to only 1 bond to oxygen with 1 additional bond to hydrogen, along with retaining your 2 bonds to carbon. And that gives you a secondary alcohol. So carboxylic acids, when they're reduced, and can be reduced all the way down to primary alcohols. Things that have 2 bonds to carbon to start with will be reduced down to secondary alcohols. And there is nothing you can imagine that would reduce readily to form a tertiary alcohol because it already has only 1 bond to oxygen. There's also no bonds to hydrogen. You notice each of these reductions involves an increase in the number of bonds from carbon to hydrogen. Now, the reverse of these reactions can also be done. That is, under appropriate conditions, you can oxidize a primary alcohol to make an aldehyde. And this is often represented generically as an oxygen in a bracket. You can oxidize something at the aldehyde functional group level, 2 bonds to oxygen, 1 bond to hydrogen, to something with 3 bonds to an electronegative element like carboxylic acid. Likewise, you can oxidize something with 1 bond to an electronegative element like oxygen and 2 bonds to carbon to something of the ketone oxidation state, something that has 2 bonds to an electronegative element. When you try to oxidize tertiary alcohols, however, or something at the tertiary, you have to break a carbon-carbon bond to do so, and it requires very, very strong oxidizing conditions. We did see one of these examples when we did our nitric acid oxidation in lab, but under normal oxidizing conditions, tertiary alcohols don't react. This is actually going to be the basis of one of our functional group tests when we start doing our qual analysis unknowns lab. In particular, if we take an oxidizing agent and we know we have an alcohol, but we don't know whether it's primary, secondary, or tertiary, we'll find that tertiaries do not oxidize, and both primary and secondaries do. So it's a way to distinguish tertiaries from secondaries and primaries. In this chapter, we will see some specialized reagents which can take things from the carboxylic acid oxidation state, which aren't always carboxylic acids. For example, nitriles have the same oxidation state. 3 bonds between carbon and nitrogen is equivalent to 3 bonds between carbon and oxygen. And reduce it, a few can reduce it selectively 1 time, but most reduce it all the way to primaries. Likewise, we'll see oxidizing reagents, and specifically PCC, that tends to oxidize primary alcohols selectively only to the aldehyde stage. But our stronger oxidizing agents like chromic acid will take us all the way to the carboxylic acid stage. We'll review reagents for the reduction of ketones, specifically sodium borohydride and lithium aluminum hydride, and we'll see new reagents for the oxidation of secondary alcohols to make ketones.